So today we're gonna talk about the limit and continuity of the function. The limit and continuity of the function, this one will be your first chapter. However, if you look at your book, it's gonna be chapter 2 because chapter 1 will be the background from your high school algebra, geometry, and trigonometry. So the most important thing that you need to review is going to be about the function. We're going to use the functions a lot in this course, and most of the time the function will be the function in single variable x. So the topic that we will include in this chapter will be the tangent problem and the area problem, the limit of the function, calculating the limit of the function using the limit law, and the limit at infinity and horizontal asymptote. And finally, we're going to talk about how to determine the infinite limit. You may take note during the lecture. I will lecture you using the slide all the time. However, for the example, you may have to write the solution down by yourself. The beginning of this chapter will be the introduction to the thing that we're gonna study, which is the limit. So the tangent line and the secant line that we have here, first of all, I like to define them. The word tangent, the word tangent derived from the Latin word tangent. So it's gonna be tangent in Latin. This guy is mean touching. So this guy is mean touching. It's gonna be that a tangent line to a curve is the line that touches the curve. So what does it look like? It's going to be if you have the curve y equal to fx below here, and you see at the point P, you be able to touch a point P with one line. Okay, so you're gonna have to touch a point P like this. So this one will be the tangent line. So this one is tangent line. Okay, so it's going to be the line that touch the curve only once. Okay, so another thing is going to be a secant line. A secant line is mean cutting. Secant in Latin mean cutting. So it's the line that cut or intersect the curve more than one time. So if you see from this picture, the secant line, you see the point P and the point Q that you be able to join them with a secant line like this. So this guy will be secant line. Okay, so in this case, you have a secant line and a tangent line. So if the tangent line is the line that touching the point P on the curve. Okay, so touching the curve at the point P and the secant line, you see that the secant line PQ. So what is the tangent problem? The tangent problem wishes to find the tangent line to the graph at the point P, and the point P has coordinate AFA. So you see that the point P here has coordinate AFA, and the point Q will have coordinate A plus H, and if A plus H plus H, if A plus H. Okay, so you have the point P and the point Q look like this, and if you find the slope that joining them, so if you find the slope of the line that joining PQ, so you recall your slope a little bit. If we have 2 points, we have x1, y1 and x2, y2, the slope between 2 points. Okay, so I think I make a mistake here. So this one must be TWO. Okay, so it's gonna be the slope that joining between 2 points x1, y1 and x2, y2 is given by m equal to y2 minus y1 over x2 minus x1. So we need 2 points in order to determine a line, okay? And if you compute the slope, so you see that the slope of this line turned out to be equal to FA plus H minus FA over, okay? So you have A plus H minus A. So in this case, you see that this guy turned out to be FA plus H. Okay, let me erase this one. I need like a more space in order to complete my sentence. So the slope turned out to be FA plus H minus FA over A plus H minus A. So in this case, this guy turned out to be FA plus H minus FA over H. Okay, so this one will give you the slope of PQ. And you see that the secant line passing through the point P AFA and QA plus S FA plus H as the slope MPQ equal to FA plus H minus FA over H. Okay, so this is how we obtain our slope. And you see that we don't need the slope of the secant line, we need the slope of the tangent line. In order to find the slope of the tangent line, we not be able to use the slope formula because we know only it's gonna be P that the tangent line gonna touch, so we not have 2 points as usual. So in this case, the thing that we're gonna do is gonna be, we're gonna use the concept of the limit. So we're gonna try to move Q really close to P. Okay, so the concept is going to be really close. So as Q approaches P, the secant line more closely approximate the tangent line, but we cannot let Q equal to P. If we let Q get really close to P, the secant line will be identical to the tangent line. And in calculus, the idea of really close is called the limit. Okay, so this guy is our guy. So this guy is called limits. Okay, and we may write the slope of the tangent line of fx at P turn out to be limit Q go to P. Okay, so the notation look like this one. Limit Q go to P. It means we are letting Q get really close to P. So it's gonna be the limit of our slope. And in order to let Q really close to P, it means that we're gonna have H, and H here will be the distance between these 2 points. So H here will be the distance between these 2 guys. And you're gonna see that if you like to have Q approach P, so you're gonna let H go to 0. So you have H approaches 0. Okay, so this one will be the concept of our tangent problem. Okay, so this one is given by your limit. And to illustrate the limit process, as Q approaches to P along the parabola, you're gonna see that if you want to find the tangent line T, okay, so my tangent line is T here, So if you want to find the tangent line, you see that you may move Q a little bit closer to P. So you have Q here, one, you have Q here, and you're gonna have Q very, very close. And you see that it's gonna make the secant line closer and closer to the tangent line. Okay. However, Q can be on the other side. So this one is Q is on the right side. Okay. Now we can have Q on the left side. So this one is Q is on the left side. So you have Q on the left and you see that you have Q here. Okay. And you can move Q closer and closer. And you see the secant is kind of approaches the tangent line. Okay, so you have right side and the left side. Okay, so that will be the very it's gonna be the very important concept of the limit that we're gonna study next. It's gonna be left limit and the right limit. Okay. The next problem that we're gonna see is gonna call the area problem. The area problem, which is to find the area under the curve y equal to fx. So you have the curve y equal to fx over the interval a, b, okay? And you are wishing to find the area under this curve. However, you see that if you subdivide this area, it's not going to be the area of the geometric figure as you have been studying in high school. Okay, so you see that it's gonna look like it's not gonna be rectangle. However, you're gonna have one side that look like a curve and you not be able to apply the method that you study in high school, because in high school you're gonna just study rectangle, triangle, okay, or maybe circle, okay. However, in this here it's gonna be you have one side of the bar here turned out to be a curve and we don't know how to deal with the area. The approach that calculus will be using can be illustrated in the next figure. So you'll be able to subdivide the interval AB into many pieces as you wish. And you see that you'll be able to compute the area of the rectangle from your high school method. So the area of the rectangle turned out to be the width times the length, basically. Okay. And then you see that this guy, you're gonna have some area that you're gonna get some error, that the area that you're not including here, the area that you're not including here, and you're gonna get some extra area around here. Okay. So you need to make the error smaller. In order to make the error smaller, you see that if you have only 4 pieces, so you have 1, 2, 3, 4. If you have only 4 pieces like this, you're gonna get high error. So you're gonna miss a lot and you're gonna get something that not gonna be even, you're not gonna get the exact area. However, if you divide the interval AB finer, so you have more than 4 pieces, you have 5, 6, 7, 8, you have 8 pieces like this, you see that the error, the thing that you miss, or the thing that you gonna get extra turn out to become smaller. So if you have 12 pieces like this one, you see that the error becomes smaller and smaller. Okay, so in this case you can have n go to infinity, so n is very large, so n equal to 1000, n equal to 10,000. You see that if you have n very large, so n in this case is the number of pieces. So if you have many pieces, in this case, you're gonna make the error become smaller, and it's gonna turn out to be the area that you are looking for. So you're gonna just compute. Okay, so you're gonna have to divide your interval AB into n pieces, like in this case, and you find the area of the rectangle. Okay, so you have the area of the rectangle that I represent in terms of A1 star, A2 star, and AN star. What is the area of the rectangle? It's gonna be just the width times the height. So if you look at this rectangle, the width turned out to be xi subtract width xi minus 1, and the height will be just fxi star. So you may pick any point between xi minus 1 and xi, and you're gonna compute the value of the function that will allow you to obtain this height. Okay, so in this case, it's gonna be fxi star multiplied with the width. The width will be xi minus xi minus 1. So you're gonna have this one is gonna be the area for this piece. Okay, so it's gonna be the green area. Let me highlight this one. Okay, so it's gonna be the green area, AI star. Okay, so this one will give you the area of the green bar here. And if you sum up all the area A1 star, A2 star until AN star, you're gonna just sum the green guy. So it's gonna be sum I from 1 to n of AI star. So you're gonna just sum the green guy. And this guy, if you take n go to infinity, if you take n go to infinity, okay, it's gonna give you the area that you are wishing for. So as n large, the limit of the sum of the areas approximating the rectangle give the desired area, okay, A that lie under the curves y equal to fx from A and B. And we may write A equal to limit n go to infinity of this sum. Okay, so we have two concepts that we have seen here. It's going to be limit n go to infinity, and you're going to have limit q go to p, or limit h go to 0. So this one is the two concept that we're gonna study. One will be the limit to the point, another one will be the limit to infinity. To infinity mean n large. Okay, to infinity mean n large. So we're gonna continue with the working example or the function that you can calculate. So you have fx equal to x minus x squared over absolute x. And you see that the function is meaningful when x not equal to 0. Okay, so you not be able to talk about f0. Okay, so you may say that in this case, f0 is undefined. Okay, so you have f0 is undefined. However, you'll be able to compute the value of the function when x less than 0 and when x greater than 0. So when x less than 0, it's going to be x equal to negative 0.5, x equal to negative 0.3, x equal to negative 0.1, and so on. So in this case, you compute fx, you get negative 1.5, negative 1.3, negative 1.1, negative 1.01, negative 1.001, and negative 1.00. So you see that if you have x less than 0, but very, very close to 0, okay, or the thing that I said earlier, really, really close to 0. So in this case, like x equal to negative 0, 0, 0, and you have many, many 0 and 1 like this, you're gonna see that it's gonna turn out to be negative. So the value turn out to be negative 1.00, and you have many 0 and 1 here. And you see that this guy will approach to negative 1, okay, when x approach to 0. Okay, so when x approach to 0, and that number turn out to be approach to negative 1. However, if it's approach to 0, it's not going to be approach to 0. It's not going to be equal to 0 in math. So we're going to avoid confusing. So we're not going to say that it's going to go to 0. We're going to say that it's going to go to 0, but it's less than 0. So it's going to be, we're going to use the superscript negative sign. Okay, so it's going to be superscript negative sign in order to indicate that the value of x not going to be 0. However, the limit side, you see that on the limit side here, it's going to be going to the number 1. Oh, sorry, it's going to be number negative 1. Okay, so this one is called the limit approaching to 0 in the case that x less than 0. In the case that x is more than 0, it's going to be x equal to 0 0.5, x equal to 0 0.3, x equal to 0 0.7, and if x equal to 0 0.7, x equal to 0 0.1, it's going to be 0 0.9. So if you not be able to imagine, let me draw you some real number line. Okay, so you have 0 in the middle. Okay, and you see that you're going to have 0 0.5 here, negative, and you're going to have 0 0.3 somewhere here, negative, and you have 0 0.1 negative here. And you see that I'll be able to zoom this one a little bit more to get 0 0.01. Okay, 0 0.01. Okay, so very bad now. 0 0.01 negative like this here. Okay, so you see that the picture turned out to be, you see that negative 0 0.5, negative 0 0.3, negative 0 0.1, negative 0 0.01, and you see that you'll be able to have something closer to 0. Okay, you'll be able to have something very close to 0 in this case. Similarly, on the right side, you have 0 0.5 here. Okay, you have 0 0.3 here. Okay, and you also have 0 0.1 here, and you have this guy will be 0 0.01. Okay, so you have 0 0.01, and you see that you'll be able to have like this number 0 0.01. Okay, very close to 0. However, it's not going to be equal to 0. In the concept of the limit, when you write x go to 0 like this, it means automatically x not equal to 0. It will mean automatically that x not going to be equal to 0. It can mean x less than 0 and x more than 0. However, it's not going to be far from 0. So this guy again that I use the word really close. Okay, so it's going to be really close to 0. Okay, and you see from this calculation that you have 0 0.01 is going to be 0 0.99. So if you have 0 0.0001 like this guy will be 0 0.999. Okay, so it's going to be very close to Okay, so it's going to turn out to be very, very close to 1. Okay, so in this case, this guy going to be very, very close to 0. However, it's going to be opposite side of the thing that we have in the previous case. So in this case, so it's going to be 0, and you're going to use the superscript positive. Okay, so this guy is going to look like this. Okay, so if you use the notation for the limit, it's going to be, you see that when x approaches to 0 from the left, okay, so this guy I'm gonna use the red color. So if you approaches 0 from the left, okay, you're gonna see that this guy will approach to, the function will approach -1. So in this case, we're gonna say that -1 is the left hand limit as x approaches 0. So this one will be the definition, and you're gonna see that this guy, the notation that we shall use will be limit x go to 0, and we're gonna use 0 to the superscript negative side in order to indicate the direction that we are approaching from the left side. The left side in this case means x less than 0. Okay, so this one is the red case. The green case here, you have, when we approaches to 0 from the right, okay, so it's going to be from the right, the value of fx approach 1. Okay, so it's going to be the value of fx approach 1, and we say that 0 is the right hand limit of x as x approaches 0. Okay, and in this case we denote by limit x go to 0. Okay, and we indicate by the positive side here. Okay, in order to give us the direction that is going to be the right side, not the left side. Okay, so we see this concept, okay, from the table. So this one that you calculate 1 and -1 here, they come from seeing from the table. Okay, so you see this guy by calculating from the table. However, we be able to graph the function. If you wish to graph the function, you may have to use the property of the absolute value. So you have absolute value of x turn out to be x itself if x is positive, and it's gonna be negative x if x is negative. Okay, and you have x can be 0 for both cases. Okay, when x equal to 0, you have absolute equal to 0 and -0 equal to 0 in this case. So you see that this guy, the absolute value of x, turn out to be two cases, turn out to be negative x when x negative, and turn out to be x itself when x positive. Okay, and you're gonna be able to get rid of x on top and on the bottom. So you see that when x negative, you're gonna get -1 plus x. Okay, and when x positive, you're gonna get 1 minus x. Okay, so this one is just the basic calculation. So we be able to graph y equal to fx as follow. When x negative, you're gonna get the yellow line. Okay, so this guy is y equal to -1 plus x. And the pink guy turned out to be when x more than 0. So when x more than 0, so it's going to be the pink one like this. And this guy turned out to be y equal to 1 minus x. Okay, so y equal to 1 minus x. So this is how we do the graph of the function. And you see that you have two sides. So you have 0 in the middle here. So this one I'm gonna highlight the color here. I'm gonna use the orange one. Okay, so you have 0 in the middle, and you're gonna have x less than 0 on the left side. Okay, so let me enlarge this one a little bit. So you have x less than 0 on the left side, and you have x more than 0, okay, on the right side. Okay, so let me write this one in the same way, x less than 0. However, they are really close to 0. Okay, however, they are really close to 0. We see also that the left limit. Okay, so if you wish to see the left limit, you're gonna see that if you are having x approaches 0 from the left side, the graph of the function turned out to be, so you see the yellow guy will approach -1, and this guy is the left limit that we talked about earlier. However, if you have x more than 0 but really close to 0, so in this case, you see the graph of the function will approach 1 instead. Okay, and this is the right limit equal to 1 that we have seen before. Okay, so this will be two concepts. And you also see that at 0, okay, at the point 0, you have a jump of the function. So you have a jump of the function. 1 is going to be -1, and it's going to be after 1 will be 1. So you see that it's going to be a jump of the function at x equal to 0. Okay, so we have a jump, okay, at x equal to 0. And the jump will allow us to conclude that the function will be not continuous at x equal to 0. Okay, so I will emphasize on the word not. Okay, so it's not continuous at x equal to 0. Okay, so this is the concept of the first example. Okay, the second, okay, so you're gonna see that, okay, another point that I wish you to consider will be the point x equal to 1. Okay, so we're gonna consider the point x equal to 1. So this guy is x equal to 1. Okay, for x equal to 1 here, you see that if you approach 1 from the left and 1 from the right, you're gonna obtain the same value here. Okay, so you're gonna obtain the same value. I don't want to confuse you, so let me try to circle my one again. So the value of the function at x equal to 1 turn out to be at this point, and this guy is gonna be 1 0. Okay, so it's gonna be 1 0 like this. So in this case, this guy at x equal to 1, if you approach 1 from the left, you're gonna approach 0, and when you approach 1 from the right, you also approach the same point 0. So at x equal to 1, okay, if you have, note that 0 is the limit of fx as x approach to 1 from both left and right. That is, you have limit x go to 1 from the left of fx equal to 0 equal to limit x go to 1 from the right of fx. So in this case, we're gonna say that 0 is the limit. Okay, so it's gonna be, you're gonna say that 0 is the limit of fx as approach to 1. Okay, so as x approaches to 1, and you denote by, okay, I think you need x here, as x approaches 1 and denoted by limit x go to 1 of fx equal to 0. Moreover, you see that the graph has no jump, has no hole like this one. You see that you're gonna have some hole here, and you see that the graph is very smooth in this case. So we're gonna say also that the function is continuous. Continuous means that you be able to walk from here to here without any skip, any jump at all. So you're gonna say that the function f is continuous at x equal to 1. Okay. The next example, you have gx equal to x squared minus 4 over x plus 2 when x not equal to negative 2. Observe that you have g negative 2 is undefined. However, we can find the limit as x approaches negative 2 by you first simplify the function. You see that x squared minus 4 can be factored into x minus 2 and x plus 2, and this will be cancelled with the bottom guy because x not equal to negative 2. Okay, so when you have x not equal to negative 2, you'll be able to cancel x plus 2 on top and on the bottom. So you have x minus 2, gx equal to x minus 2. Then you have the limit x go to 2 from the left and the limit x go to negative 2 from the right, okay, will be just negative 4. How would we see that? Because if you graph this guy, okay, I'm not seeing this guy right away, so you just graph y equal to x minus 2. So this guy is y equal to x minus 2. And you see that you're going to have problem only at x equal to negative 2, which is one whole here. Okay, so you have one whole here for negative 2. Okay, so you have one whole here for negative 2. And you see that when x approaches negative 2 from the left, your graph will be approaching negative 4. Similarly, if you have x approach negative 2 from the right, you're going to have your graph approaching negative 4. So you have the left limit equal to negative 4, the right limit equal to negative 4, and we're gonna say that the limit x go to negative 2 of gx equal to negative 4. But we have a hole. Okay, so we have a hole at x equal to negative 2 on the graph. Okay, so we have a hole at x equal to negative 2. So in this case, we're gonna say that the function g is not continuous at x equal to negative 2. So not continuous can happen in the way that you have a hole on the graph like this, or you have a jump on the graph. Okay, so you have a jump on the graph or you have a hole on the graph. Okay, so this one will be the two examples that I want you to see the function that not continuous into different way. Okay, and you be able to see that this guy, the limit exists because the left side equal to the right side, And in this case, the limit does not exist because the left side equal to -1 and the right side equal to 1. In this case, we're gonna say that limit x go to 1 of fx does not exist. Okay? And we're gonna talk about in the general form. If you have a in the middle, if you have a in the middle, you're gonna have a here, and you have the left side. Okay, this one is x less than a, and this one is x more than a. So you have two sides, and in the left side you're gonna use the notation x go to a from the left. The right side you have x go to a from the right. Okay, so you have limit x go to a from the left of fx equal to L. This one is the notation when you have the situation that the value of the function will approach to L if x is really close to a, but x less than a. Okay, and in the case that x is really close to a and x higher than a, the notation will be limit x go to a from the right. Okay, so this one is called left. This one is called right. Okay, so this one is right. Okay, and this one is called right. I choose have IGHT right. Okay. And if you have the left limit equal to the right limit, you're gonna have another notation for the limit that the limit from the left equal to the limit from the right. So we're gonna just write down limit x go to fx equal to L. Okay, so we just write down the limit x go to fx equal to L. Okay, and we're gonna have f is continuous at a. So f is continuous at a means that you have the function is defined at a. Okay, and the limit x go to a of fx exists, and limit x go to a of fx equal to fa. Okay, so this one will be the limit and continuity of the function. Okay, let me conclude everything from the graph first. The graph of the function and continuity. So you're gonna have f is continuous at x equal to a. So you see that the graph will look like this one, and you'll be able to walk along the graph, okay, at the point A without any jump or without any hole. So let me just write the thing that we notice here. So this one is without any jump or hole in this case. Okay, so it's continuous. The thing that we have seen is going to be in terms of the limit is going to be fa equal to L, limit x go to a from the left of fx equal to L, and limit x go to a from the right of fx also equal to L. Okay, so this one, you see that limit x go to a of fx equal to L equal to fa. So this will be only one case that our function turned out to be continuous. Okay, so this one will be our important condition. Okay, so continuous at a means limit x go to a of fx equal to L equal to fa. Another 4 cases will be the function that you're gonna see some jump, some hole. In this case, in the second picture, you see that you have x go to a from the left and x go to a from the right. And you see that the graph will approach to L, both sides in this case. So you have limit x go to a from the left of fx equal to L and limit x go to a from the right of fx equal to L as well. And you have limit x go to a of fx can be conclude that limit equal to L, but the function is not equal to L at a, the function equal to m, not equal to L at a. So in this case, you see that this guy is not continuous at a. So it's going to be not continuous at x equal to a. Okay. And for number 3, you see that the function has limit at x equal to a, limit from the left equal to L, limit from the right equal to L. However, the situation here in this function will be fa will be undefined. Okay, so you not have the value m as before, and the value m is not here, so it's not continuous. Okay, so this guy also is not continuous at a. Let me just copy. Okay, so just paste this guy, and it's not continuous at a. Okay. Similarly, for this one, you see that this one is kind of, you have a jump. Okay, so this one, maybe I say you have a hole. Okay, so you have a hole. Now you see that you have a jump. So you have a jump at the point A, and you see the left limit equal to A, the right limit equal to B, and A does not equal to B, and the value of the function is equal to M. So this is the situation in this picture. And another last guy, you see the left limit equal to B and the right limit equal to A. Okay, I make mistake here. Let me erase this one. I switch this one a little bit. So this one is not A and B. This one will be B limit from the left and A accordingly. Okay, so the function is undefined at a, limit x go to a of fx from the left equal to b, from the right equal to a. Okay, so they are different. So the limit x go to a of fx does not exist in this case. Okay, so you see the situation that here. Let's do this example. I will give you some time to do this example on your own first. Okay, so I give you about 1 or 2 minutes. I'm gonna wait, and we're gonna do this one together. So you see the function y equal to fx on the interval -3 to 3. Okay, the question gives you, the question asks you several things. So it's going to be the function is continuous at every point except when, okay, and f0 equal to what, f1 equal to what, f2 equal to what. So you have to be able to determine them, and you're going to compute the limit. Okay, and some limit will be does not exist. Okay, I wait you a little bit. we almost done for this script. Okay, so for this one, you have y equal to fx on the interval -3 to 3, and the function is undefined at 3. So you see that it's undefined. So you have the hole here. And the function is continuous at every point except, so you see that it's going to be some jump, some hole. And you see that at 0, you're going to get jump. Okay, let me just write j. Okay, and here at 1 you're gonna get jump also. Okay, and at 2 you get hole, and at 3 you don't care because 3 is outside our domain. Okay, outside the domain. So in this case, you're gonna have the function is continuous at every point except x equal to 0, 1, 2. Okay, and f0 equal to 1, f1 equal to 2, and f2 equal to 1. Okay, so this is how we determine them. And you have limit x go to 0 from the left turn out to be, okay, so let me use color here. So it's going to be number 2. Okay, and the limit x go to 0 from the right, okay, it's gonna be 1. Okay, and the limit x go to 0 of fx will be does not exist. Okay, and limit x go to 1 from the left. Okay, limit x go to 1 from the left, you see, go to 1 from the left, look like this guy is gonna be 1. Go to 1 from the right, okay, the green guy go to 2, and limit x go to 1 of fx again turn out to be does not exist. Yeah. Finally, you have limit x go to 2 from the left equal to 2, and limit x go to 2 from the right turn out to be 2 as well, and the limit x go to 2 itself turned out to be equal to 2. Okay, so I use color to indicate left and right. Okay, so the left side I use the orange one, and the green one I use it for the right side. Okay, so this is how we determine the limit from the left, from the right, and the limit at the point by using the graph of the function. Sometimes it's not quite convenient to do that because you not be able to know the graph, or you not be able to sketch the graph. And actually we study cal because we want to be able to study to sketch the graph. So when you have this thing, we gonna study the way or the other ways to calculate the limit. We're gonna study in the next clip. It's gonna be calculating the limit by using the limit law, okay? And it's gonna be involving many algebra. Okay, so I'm gonna first stop here for this first clip, and we're gonna continue next time.